plus On. This is going to be, so what can you do when you do big O analysis? You can drop the low order terms. On is much, much bigger than log n, as we showed just now. This part drops off, so this is going to be On. Alright, so that's how we do the analysis. So there are a little bit of, I'm playing game doing abuse of notation, right? Remember these are sets. I'm using a plus on a set. What the hell does this mean? How come I'm able to plus two sets together and then just drop out the rest of the numbers? This doesn't make sense, right? If you think of it from a definitional perspective. So when I use plus, when you're using these kind of equations using big O, what this means is this is some function CGN, right? In this case, it will be Cn, right? Some function Cn, right? I don't care what function it is, but it's a function Cn, right? And this will be C log n, and this will be, let's say C1, let me be more precise. This is C2, and let's say this is 3. Okay? And we know that this one will be O of n, right? So this is what this means, right? It means some function, right? Okay, so our problem is solved, right? Not quite. So, boss goes to the office, calls Homer actually, and says, you're fired, right? This bug, there's a bug in your code. It's not working, right? So our wonderful algorithm just now is wrong somehow. So, but do you think it's wrong? Is something wrong with this algorithm, this particular algorithm? So A, yes, B, no, boss is dumb, or C, is this a trick question? So what do you think? Do you think there's something wrong with this particular algorithm? Boss says there is. Do you think there is a problem with this algorithm? So put in your answer, let's have a look. A, yes, no, boss is dumb, and C, is this a trick question? So what do you think? I'll let you look at the code again. Okay, again, think about it carefully. What could be wrong with this particular piece of code? Right? Something's not quite right if there is a bug. If there's no bug, then it's fine. What do you think? So let's have a look. Lots of people are saying yes, there's something wrong. A few people are saying no, boss is saying no. And some people think it's a trick question. Alright. So let's switch it here. Okay, we have 40 mark. Let's have a look. So let's see. 61% of you have gotten it right. There's something wrong. So can anyone tell me what's wrong? Sorry? Okay. So can you repeat that so everyone can hear?
Multiple of the same cost, the same spending.
The same spending. Okay, so let's have a look. So imagine this situation, all right, where multiple people have spent $11. Okay, what happens in this situation? So I find everyone who spent $11. What happens to binary search here? It returns this point, right? It just returns this point immediately. And then when I print out from A to B, let's say B is 28. If I print out B, I'm going to miss out all these people here. Okay? So that's a bug. I have a bug in my code. So this is wrong. Obviously, this is wrong. How do I fix it? So what do I want when I clause start? What do I want? Do I want find index? Find first index. I want to find the first index. Right? I want to find the first customer who spent $11. How about the second thing, the end? Do I want the first index or the index? What do I want? I want the last index. Okay, so that's what I want. I want the first index, I want the last index. Okay, so let's talk about first index. Last index is very simple. Let's talk about first index. They're like kind of symmetric. Okay, so let's look at first index. Here's the question. How can we modify binary search to find the first index? Alright, so what's a simple way that we can do to modify binary search to find the first index? So what's the most straightforward way you can think of? Let's say, bam, you hit some value, right? Where is the first index? Is it to your left or to your right? Left. Okay, so what can you do? What's the easiest way? You search left, right? You keep going. Let's say one way to search left is just to go one by one until you find the first instance, right? So this is example, right? You do binary search first, and then once you find it, you just keep moving. You do search left until you find the first index, right? Of the 11. That's it, right? That's one way you can do it. What's the time complexity for this algorithm? ON, correct? ON. Why ON? Because let's say you hit the midpoint, it might be the case that 11 is all the way here, right? The first person is 11, and so you have to do ON, so you did n over 2 times, which is ON, right? That's the worst case. Can we do better than this? Can we do better than this? So what can we do?
Just speak the death again.
Binary search, great, binary search. Let's use binary search again, alright? So, we know that index may be the first occurrence. So here, this value, it may be the first occurrence, or we're not sure, alright? If we're not sure, do we search to the left or to the right? We must search to the left, right? We can still get rid of half this array. This part, it cannot exist here, right? It must exist on this side. So we're going to explore a candidate result. We say, okay, it may be 5. It may be this one, right? But we're not sure yet. Let's keep looking. Okay, so you keep looking. We're going to pump here, right? Okay, n equals to 2. Say, okay, this is not it. Let's look again, and this value got 3. We're going to update our candidate result. Say, okay, 3 is less than 5, so that's going to be our updated candidate result. And then you're done. Okay, so you're just using binary search again. So what's the worst case computation complexity of this algorithm? Is it log n, linear time n squared, or O1? What is it? Let's go. So this one should be straightforward. We've analyzed it for binary search. What do you think this is? Is it log n squared, or O1? For the worst case computational complexity. So I think most of you are going to say log n, yeah, 22, none of the numbers are here, it's just at 100%. Alright, good. Oh, someone said 1 squared. Guys are just messing with me. Okay. I think most of you know that it's O log n, right? It's O log n because it has the same computation complexity as binary research, right? Good. We have to search our correctness a bit. We're going to set the precondition, right? As Amin is the first occurrence of the key if you're doing binary search first. Okay? Alright. To do find last index, what do you have to do? Instead of searching left, you search right. It's very simple. Very straightforward. Okay, you guys can figure this out. You don't need me to leave you through it. Right? There is another bug, right? There are other bugs. Okay, it's simple code, so Homer is not the best coder around. Here's some other bugs. What if the end or start of n is not found for this code? It doesn't really make sense, right? So you can fix that. You have to do proper checking, or maybe you can modify binary search to return the next largest or next smallest item. Alright, so maybe you can think of how you can do that for binary search. Okay. Okay, so writing correct programs, this idea of writing correct programs, as I mentioned, was in this book, right? Programming Pearls. It's a very famous textbook. The binary search, he does a whole chapter on analyzing binary search to prove that it's correct in this book. Alright? And this version of binary search was used in the Java SDK, so very widely used, except there was a problem. Despite proving that it's correct, there's a bug. There was a bug in the Java SDK, and it was very nicely written about in this blog post. So if you want to read about this blog post, you can find it online. Okay, it's by a Google AI researcher, short blog. He talks about his time knowing John Bentley at CMU. Okay, so what is the bug? What is the bug? Oh, by the way, you can read about. I posted the John Bentley's article on Piazza. So if you want to look, you can find it here. Okay, writing in extra readings, writing correct programs. You can read it if you want. Okay, it's a little article. Nevertheless, there's a bug. What's the bug? What's the bug? Which line do you think has a bug? Looks good, right? We proved it correct, but there's a bug. And the bug went unnoticed for many, many years. I think 2 decades, was it? 2 decades, if I'm not mistaken. Yeah, 2 decades. 20 years, no one discovered this bug. Until it started breaking. So what did it break? The problem is here, this line. The problem with this line is that it can overflow if low and high are very large. If these two numbers are very big, this overflows. And then mid no longer is valid. Right? You get the wrong middle point because it has overflowed. Right? So this is a bug with this particular line of code. Does anyone know how to fix it? How can you fix this line?
Let's go.
Can you fix it?
Divide by 2.
So there are multiple ways. This is one.
I don't know what.
We take low,
Yes.
and we don't add them together, we minus.
Algebra.
Okay, so I minus low, we do this together.
Oh, yeah, makes sense.
Right, so
Makes
this
sense.
is one part
Suddenly
of
makes sense to me.
this code. But yes, so this was to illustrate something. Is to illustrate that writing correct code is actually extremely difficult. Okay, even John Bentley, who had this entire book and like chapters on how to write program, got it wrong for this particular piece of code, and the Java developers didn't even notice it. Right, so please keep in mind that it's very difficult to write correct code. Okay, so our problem is now really solved. All right, till someone finds the next bug. But yes. Okay, so let's talk about the summary. We've talked about divide and conquer. We split into subproblems, we solve the subproblem and combine them together, and we have to be careful with programming parameters. Okay? So any questions at this point? Okay. So let's move on. So last week we talked about insertion sort, right? So an horizontal sort is an insertion sort algorithm, and it's too slow. Right? You have more than 1 million customers. It's getting way too slow. You need a better method. And so we're going to apply divide and conquer to the problem of sorting. So we can apply divide and conquer. Remember, we're going to split the problem, we're going to solve each problem recursively, and then we're going to combine the solutions together. Okay, that's the strategy. Let's look at how we're going to do that in merge sort. So this is a merge sort algorithm. I'm going to split this up. So not knowing anything more, how should I split this up? What's a good way? Halve it? Okay, I halve it, right? I'm going to split into 2 parts. So imagine that like I said before, if you do things recursively, imagine you have this magic algorithm that kind of does it for you already. So I'm going to solve each part. Okay, I'm going to call sort on each part. And these two are going to solve it together. Each part will be solved, become sorted. Okay? And then after that, what do I have to do? As in the name, it says merge sort. So I'm going to merge them together. Okay? I'm going to combine the results into one array. So I have these two small arrays of sorted elements, and I'm going to combine them together. And this is the algorithm for merge sort. It's extremely short, as you can see. Very short, very simple. What do? I basically recursively call merge sort, right? All I'm going to do is I'm going to split it, I'm going to solve it, I'm going to continue splitting it and solving it all the way through. Okay? Merge sort, merge sort, merge. That's all I'm going to do. Merge sort, merge sort, merge. So let's see how this algorithm works, right? I'm going to split it down the middle, and then I'm going to continuously split it down the middle. Okay? And then at some point, I'm going to have basically atomic elements, right? One element in each cell. So once I'm at this stage, is this array sorted?
Yes.
Yes, trivially sorted, right? There's only one element, so it must be sorted. So now I'm going to merge upwards. So I'm going to take these two, I'm going to merge them together. So now I'm going to get 3 and 7, right? These two I'm going to merge together, so I'll get 5, 9, so on and so forth. Then I take these two, I'm going to merge them together. I take these two, merge them together, and I merge all the way up. Okay? So that's merge sort. Okay? You decompose it all the way down, and you merge it all the way up. So of course, the key step here is the merge algorithm, right? What are we doing to merge? So merge is actually very simple, right? It's very straightforward. Let's go through it step by step, and then you can see how it works. Okay? So for the merge step, imagine as though I have these two parts, and they are both sorted already. Okay? I've already called merge sort on them, so if you return it to me, this is what I have. How can I merge these two together? So one very simple way is to consider, I'm going to, let's say, I'm going to put it into some array, alright? So I'm going to look, let's say I'm going to put this I, I'm going to call this J. Okay, and we'll call this K. Alright, so what I'm going to do is very simple. I'm just going to compare what's at J and what's at I. Alright, and whichever one, which do I take? The smaller one or the bigger one? The smaller one, of course, right? And so then I'm going to increment J. Right, and I'm going to increment K. Now, what do I pick? I compare the 3 and the 2. I take the 2. And then I increment again. Okay, now it's 6 and 3. Which do I pick? Obviously, I pick the 3. And I move the I. And I move the K. Oops. Okay. Alright? And okay, I'm not going to do this all the way to the end. You can imagine how it works, right? You just keep incrementing I and j while filling up this new buffer array of the sorted elements. Okay, very, very straightforward. So the merge step is very straightforward. This is the pseudocode. I won't go through it, right? You can read on it on your own. It's not difficult, but it's slightly different than the one I presented, meaning that you first copy everything to a buffer array. Alright, so it's just slightly different. You can work through it slowly. Okay? So, is this code correct? So, to verify it's correct, what you need to do is to set up your initialization. Make sure this is the main loops that we are concerned about. So, set up your precondition, right? Set up the loop invariants. Work through it step by step, and then you figure out whether it's correct or not. The big question, of course, is what should be the loop invariant. So let's look at this particular loop here. What is the loop invariant? What is the key idea behind the merge step? What's the key idea behind the merge step? So imagine if I'm copying everything to some, I start off with some buffer, right? And the buffer is some midpoint here, so this is the buffer. I'm copying everything to this new matrix A. Okay, I'm going to copy things step by step into A. Alright? So what is it that I want to make sure? So just now I have I and J. Let's say I at some point I is here and J is here. Okay? I points here, J points here, and let's say K is here. Alright? So what can I say about this part of A? Is sorted already, right? So that's what I want to preserve. That's my loop invariance essentially. I want to preserve that anything that is A less than K, right? Less than the index K should already be sorted. That's what I make sure. I also need to make sure that everything from I, like less than I, has already been copied over to A. Anything less than J has already been copied over to A. Alright, so that's what I want to be sure. And that's its idea here, right? Basically setting left is the left side of the buffer, right is the right side of the buffer, and then I want to make sure that low to k minus 1 contains all the smallest elements of L and R in sorted order. Okay? And then L and R contain the smallest elements of their respective arrays not yet copied to A. Alright, so that's the basic idea, very simple. I'm not going to do this here, it'll take too much time, but you can go home and just verify the loop invariant holds at each iteration. Okay? It's again, not hard, just a little bit tedious to go through. Okay. So what's the worst case time complexity for merging? Is it A n log n, B o n, C o n squared, D o1, E I? We should stop asking all these complexity questions. So which do you think it is? Is it for merging? Okay, so look through the algorithm. What is the worst case time complexity for merging? So let me. So remember what merging does? Merging, you have this array, right, split into two. You're looking at each element one by one and copying them into a new buffer.
Because
right?
n log n level you are merging one time. And then the merge is n. So it's n log n.
Okay, so more, look, we're not there at 26. Okay, 26, 28. Is it just me or is today very, very cold in this room? Cold, right?
Do you code it?
Okay, talk to the facilities guys.
Okay. Hair got ice.
So we're at 35. Most people are picking ON. Some picking ON log n, and some people are saying I should stop asking these complexity questions. Okay, let's have a look. The right answer is ON. Alright? So why is it ON? Let's take a look again at this code. Right? Why is it ON? So look at what the code is doing. It's just looping through this. This is the main while loop, right? This just finishes it off, but this is the main while loop. The while loop just looks at each element once, right? You're just comparing, right? And then you're just moving, you're just copying every element once, right? So you touch every element once, it's ON, right? You don't really need ON squared or ON again because you're just touching, you're just copying the elements one by one into this buffer array, okay? So that's why it's ON. Okay, so merge sort. What is the running time for merge sort? Now we're getting to the crux of it. We've talked about merge. Let's use the result for merge and think about how long merge sort takes. Is it A n log n, B o n, C o n plus log n, or D is too hard, I sleep now? Okay, what do you think? So put your answer in. Let me change it first.
N plus log
Okay.
N.
Okay. So put the code up and you can see.
Then you can take away the log N.
How about what's this kind of objective for merge sort? Right? So again, don't just like hunt down one answer, alright? Think about it. Try to work it out. You actually have all the tools you need to actually work this out from the algorithm analysis class that we covered last week. Alright? So think about how long this will take. And then I'll give you a minute. Alright, a couple minutes.
I hope the PS is easy.
I'll show you
I wouldn't like
what we can do.
all the edge cases very weird. Like, you need to think properly, like all these indexes kind of thing. You need to think of index like fucking hate it.
Couple minutes.
Mother going to die. Come on. Don't disturb me, I'm having my life. You don't cut right? Same right? Yeah. The scale right, the scale right in China, 就是新加坡锦鲤。Thank you, like, I see him for 7 years already.
Again, when you don't know how long it takes, break it down into the individual function calls. Think about how
People so smart and
long
tired.
each one takes. Think about the structure of the algorithm. Write out the recurrence relation.
Mà không biết yeah, that's it, there's the only one. That's the only one. And you know when broken, he come from China as Sec 3. Mà không chờ nè, mà không chờ. My PS Junker came in the same scheme as Ma Hong Qiang. So they're the same kind of, like they're not famous about the same kind of scheme, the Sec 3 China boys. Yeah. Because he was only called for NS at year 3 of NUS. Because they miss it, because he converted PR like before he went NUS, I think. Like, I think there's a window we created PR, then probably the people fuck up. During NUS, so they call him right, then he report to Tekong like next day. I don't know why he don't report, he just a good boy.
Okay, time's up. So majority, 80% of you have said it's O n log n. Smaller number have said it's sleeping. And then some of you are saying it's O n. I think maybe one person saying it's n plus log n. Okay, so let's look at this. The right answer is, unsurprisingly, 80% of you got this is n log n. Right, that's the answer. Of course, the big question is why? Can we derive an answer? Now, why is it that I'm making you derive all these numbers? Is because for most short, I think most people kind of can guess an answer. But very often in real life, you're going to facing algorithms that you have never seen before. It's very important for you to develop this skill in order to derive the worst case performance values. Alright? So let's look at this algorithm. Let's go line by line and look at how long each one takes, just like what we did last week. Okay? So this is, let's say let's take this one. This takes how long? Does it take n time? How long does it take? Just this line. Just this one line. One. Takes constant time, right? This line? Constant time. This line?
Just cut off.
How long does that take? This one calls A from low to mid, and this one mid to high, right? If merge short is Tn, so this is taking, this will take some constant time, let's say this takes some constant time. This takes, what goes in there? N over 2, good. What goes in there? What goes in here? N. Okay? So that's what it looks like. Okay? So if you add all this up together, you get something that looks like this. Right? That's going to be your recurrence relation. Right? That's your recurrence relation. And you know how to solve this. We've done this before, right? Last week. What you need to do is keep substituting inside until you derive a general relation. And then you solve the K. right? And you plug it back in. Right? That's one way. There's another way you learned last week, which is the substitution method. What's the substitution method last week we learned? You make a guess, right? You make a guess, let's say n log n. You substitute the recurrence relation, you prove it using mathematical induction, and then you prove the base cases. Alright, so that's the technique that we learned last week. You can show it quite easily. I'm gonna, let me see. So let's just say you make a guess that is O n log n. Right? You substitute inside. So in this case, we're saying that you make the inductive hypothesis that Tn prime is less than Cn prime log n prime or okay, that's what you want to show. So what you're going to do is you are going to say that this is smaller than or equal to 2
map module one.
over 2 log n over 2 plus Cn.
Competitive basis.
Okay, and then you can just write it out line by lines, log n over 2 plus Cn. Go all the way down, you will find that you can show that this is this. Okay, and then you just show for the base cases. Right? So remember that for mathematical induction, what you want to show that this is the case, right? You prune it for, you assumed it for n prime less than n, you show it for n. Right? So that's the idea. Okay, so I'm going to show you a different technique now, because in this case, we made a guess, right? We made this kind of guess, right? How the heck did we come up with a guess? Right? How do we come up with a good guess? Now, the good way you come up with a good guess when you look at this kind of recurrence relations is to use something called a recurrence tree. Alright, so you can see that merge shot does this recurrence downwards, right? This looks a bit like a tree, right? It breaks into 2, breaks into 2, breaks into 2, 2. So let's look at how much computation this takes in total, right? From a tree perspective. So this is how it looks like. At the top level is Cn, right? This Cn comes here. This will take Tn over 2, and this will take Tn over 2, right? I'm just taking each part put here. And then we'll break it apart again. So this now will take Cn over 2, right? I'm just plugging n over 2 into the previous equation here. Right? So this is Cn over 2, this is Cn over 2, and then it breaks apart again. Right? We keep breaking apart till we get to some number. It goes all the way down, but I won't show it over here. Right? Let's go to Cn over 8, because that's as much space as we have on the slide. And let's see how much time each level takes. So each level, this level takes Cn, this level takes Cn, this level also takes Cn, all the levels take Cn. Okay, that's how much work is done at each level. The question now you have is how deep does it go? How many levels do I have to go up? Right? So this is the recurrence, right? You see at level 0 you have 1, at level 1 you have 2, level 2 you have 4, level 3 you have 8, level 4 you have 16, right? So you have this kind of relation, right? N equals 2h. Alright? So this is the number, right? And this is the level. So does this look familiar somehow? Have you seen this before? You should. We just solved it. Right? We just solved it in the early part of the class. Okay, for my research. We said that this n over 2k equals to 1. Is this. Right? And you now we know it's log n. Right? That's what we know it's log n. So we do the same thing. H equals to log n. So how many levels does it go? It goes log n levels. Right? It goes log n levels. So that means that here what we're going to do is we're going to sum up all the work for log n times. Right? We're going to sum all the work for log n times, and that's going to give us Cn log n. Because log n levels, so log n times Cn, right? Because each level is Cn work, and we do this log n times, right? So that's going to be Cn log n. So this is going to be our bound. This is equivalent to O n log n. Right? So this is how you can formulate guess. If you do this very precisely, you can actually this can form a proof also for how much time a particular takes. Okay. So the right answer is n log n. So now you know a new technique for deriving for this kind of recurrence relations. Okay. Okay. So that took a bit of effort, but you now know that word short is an log(n), alright? And the derivation basically requires you thinking through the steps and breaking down the recursive calls, and then you sum up all the costs at each level, and then you figure out how many levels you
I
need to
try to
go.
do, but
Alright, so that's the basic
I
idea.
don't have anything to add.
Here's an extra question, okay? Can we do better than n log n for comparison-based sort? What do you think? So how many people think, yeah, you can do better than n log n? How many people don't think no? So how many people think yes, you can do better than n log n? Comparison-based sort. How many people think no, you cannot do better? No. Okay. So the right answer is, here's the hint by the way, the hint is in this figure. Right? The hint is in this figure. Alright, so the right answer is no. Alright, so if anybody in the future, let's say you become a boss of a multi-billion-dollar software company, or invent some cool, I don't know, AI algorithm or something like that, don't forget, first of all, don't forget me, right? Remember that I got you some of this stuff. Remember me. But also, if you're ever such a boss, and one of your employees comes to you and says, I have a brand new comparison-based sorting algorithm, it performs in linear time. You can tell the fellow to go fly kite, right? Because you know that this cannot be true. Alright? Why is this not true? So the hint, as I said, is in this plot. Okay? So let's try to understand why this plot works. If you want more details, I'm going to give you a hand-wavy argument. But if you want more details, you can look in chapter 2 of Strategy and Weight or the CLRS book. Okay? Or just wait for 320. We'll cover that later. So let me give you the key idea. So what do sorting algorithms do? Sorting algorithms, what they do is they permute the array in some way so that it's sorted. Right? Now, that means that any correct sorting algorithm has to work for any kind of input. Right? It has to work for any kind of input. Alright. How many possible permutations are there of sorted arrays? We've covered this before. It's n factorial. N factorial number of permutations. Now, a sorting algorithm can be viewed as abstractly as a decision tree. So what do you mean by decision tree? Let's look at this diagram. So this decision tree helps the sorting algorithm figure out which permutation to output. Okay, what is the correct permutation such that the array becomes sorted? So this is how it works. I'm going to first check, oh, is A less than B? If A is less than B, then I check, oh, is B less than C? If B is less than C, that means the correct thing is A, B, C. Alright. If, for example, A is less than B, but B is not less than C, right? Then I check, oh, is A less than C? If A is less than C and B is not less than C, then it's going to be ACB. Alright? So you can go through this and you can see that this decision tree is correct. What this means is that the sorting algorithm has to figure out this decision tree, right? Must work for every possible input. And you know that there are n factorial possible inputs. That means the number of leaves, these are the leaves, we'll cover more about leaves later. Basically the terminal point of each of these decision paths leads to a leaf. And this leaf, there must be n factorial of them. Right? For them to output n factorial possible outputs, there must be n factorial of them. So the number of leaves in the tree must be larger than n factorial, must be smaller than 2 to the power of h, where h is the height of the binary tree. So in this case, we just have to take logarithms again, right? Where the height of the binary tree must be larger than log n factorial, and you can show that this is lower bounded by n log n, right? Using Stirling's approximation, which you can read about if you want to read about. Okay? So this is a hand-wavy argument, but you can, if you really are keen to know, you have a theoretical stint to you, just check it out. Okay, it's a very neat little proof, and it's also very useful. It's one of the more useful theoretical results out there because, for example, you can tell your employee to fly kite if they come up with a linear algorithm. Does that mean that linear time sorting algorithms don't exist? Linear time sorting algorithms do exist, right? But they're not comparison based. They don't rely on comparing two numbers and two numbers only. Okay? So there are things like Reddick sorts, for example, or Conky sorts. They are not comparison-based sorts. Let's look at some real-world performance. This is bubble sort, our quintessential bad sorting algorithm. This is selection, this is insertion, and this is merge sort. Right? Merge sort is way faster than all the n-squared algorithms that you can learn. So great, your sort is fast, you get promotion bonus, and now you know how to apply divide and conquer. Right? You know it in two particular methods, binary search and merge sort. Alright? And hopefully when you see new problems, you can apply the same strategy. right? And you now can analyze the performance of virtual environment research, and you know a little bit more in terms of how good you can actually do for a comparative based domain. Okay, divide and conquer. Again, don't panic when you face a complicated problem like a differentiation. You break down the problem and you build up a solution from the cases. This is also divide and conquer. Divide and conquer is very widely applicable to all areas of life. Right? So I would encourage you to apply liberally. Before the next lecture, please cover quicksort. Okay, you can cover a little bit more, but at least cover quicksort. That will be tomorrow. And you can do optional stuff. Are there any questions before we break? Okay, so there are no questions. I'll be here if you want to come down. Simply, you should revise your quicksort before tomorrow. Okay? Alright, see you guys.
It's between these two mods already. But because ES can actually, I think ES got for what? Oh. Say bye.